Cañadas from Universidad Nacional de Colombia, and he's going to tell us about wargaming with quadratic forms and Brauer configuration algebras.
Thank you very much for the presentation. First of all, I would like to say thank you, Slava, for the kind invitation to this meeting, for giving us the opportunity to say something about our work in Colombia. And thanks also go to the ICTP staff for the kind logistics and hospitality. For me, it's very nice to be here. Thank you very much to all. This is a joint work with Pedro Fernandez and Gabriel Bravo from the National University of Colombia. They did his doctoral studies there in Bogota. So this talk is dedicated to the Ukrainian people who is suffering the consequences of an infamous war. And for us, it's very important to know that. As a motivation, let me tell you that this thought is a way of refusing some hardest thoughts regarding the role of mathematics and number theory in particular in warfare scenarios. According to Hardy, mathematics, and in particular number theory, don't deal with warfare scenarios. But nowadays, we know that there are several applications of mathematics and number theory in warfare operations. For instance, cryptography is an example of the use of mathematics in warfare. In this talk, I will try to describe you how we can use some interactions between the theory of representation of associative algebras and the number theory, in particular the famous Cauchy polygonal number theory, and some famous conjecture proposed by Ramanujan in 1917 regarding universal quadratic forms. The idea is to use all this machinery in order to describe a war game based on a behavior of a missile defense system. This is the roadmap of the talk. Firstly, I will describe something about, briefly, regarding quadratic forms and their relationships with the theory of classification of associative algebras as Irina described yesterday in her talk. And secondly, I will describe Berg-Constant gain. Berg-Constant gain was introduced by Postnikov in 2018 at the NIT in a series of lectures defined by Postnikov. He defined several gains, in particular Berg-Constant gain. And the idea is to apply some interactions between Berg-Constant gain, and we can see how this gain can be used in order to classify finite algebras, finite associative algebras. Thirdly, I will describe Brauer configuration algebras, but Pedro described Brauer configuration algebras last Monday in his talk. And fourthly, I will describe our war game, where we fire admissible paths. And the idea is to declare winners and losers in this war game by using the Cauchy's polygonal number theorem and the Ramanujan's problem regarding universal quadratic forms. Let me tell you that quadratic forms, the theory of quadratic forms, their classification, and the way that we can use roots of quadratic forms is a very well-known subject in mathematics. Several Ukrainian mathematicians have described the structure, for instance, of the roots of quadratic forms, of Tsienko, Droz, and so on. There are many Ukrainian mathematicians who describe the structure of positive roots. And this is one of the reasons that I choose this talk. So quadratic force, we can define a quiver, and any quiver has associated a suitable quadratic force. It is very well known, this result. And also, we know that there is, as Irina described also yesterday, there is the homological quadratic force associated with the quiver. And this quadratic force, the quadratic force associated with the quiver, and the quadratic force, and the homological quadratic force coincide in the case of an acyclic and connected quiver. And we had here an example of the linking diagram of type A2 with two vertices. And this is the list of positive roots. This is the maximal root associated with this quiver. It is also very well known that we can use the Weil group and the Coxeter transformation in order to obtain a bijection between the dimensions in decomposable representations of a quiver, of a linking quiver, and positive roots. And this is the case when we can use the elements of the Weil group in order to describe the different positive groups in the example that I described before. In particular, Gabriel proved that we can use Coxeter transformations, the Weil group, in order to describe a bijection between the dimensions in decomposable representations of an acyclic or a quiver or linking type and the corresponding positive roots. It's possible to define such a bijection. Actually, as Irina yesterday said, the algebras of finite representation type are those of linking type AN, DN, or E6, E7, or E8. This is a well-known result in the theory of associative algebras. Bell-Constant game is a game proposed by Postnikov in a series of lectures given by him at the NIT. And he defined several games, several interesting games, combinatorial games. But in particular, this game, Bell-Constant game, which consists of giving chips to the different vertices of a simple graph. And the game starts with all the vertices without chips. And the idea is to distribute chips to different vertices in the graph. Such a way that we define a configuration where this number Ci here is giving information about the number of chips that the given vertex has in the quiver, in the graph, excuse me. In such a way that vertices in the graph can be happy, unhappy, or excited, according to the number of chips that the given vertex has in the graph. Okay? What is the idea? The idea is to give chips to all the vertices in such a way that all of them are classified as happy or excited. The game ends sometimes. Okay, the idea is giving vertices by using this kind of reflection. As you can see here, initially no chips are present. Ci equals 0 for all I, and all vertices are happy. Then we place a chip at the vertex, at the given vertex, 1, So these vertices, I0, is excited, but neighbors are unhappy. This is the way that we can play the game in the case of a linking diagram of style A4. As you can see here, I choose this third vertex to get the first chip, and the game ends with the maximal positive loop of this linking diagram. So, sometimes the game never ends. For instance, if you use an Euclidean linking diagram, this is A4 tilde, the game never ends. We start assigning chips to the different vertices, and the vertices never ends, and the game never ends. And Postnikov proved that this is the case. This is the case. Firstly, that the game doesn't depend on the moves, doesn't depend on the vertex where the game starts, in such a way that the game is well defined.
Could you go back a little bit? Just finish reading the statement. No, just the statement of the theorem.
This is a way that Postnikov described that the game is well defined. Actually, as you can see here in this theorem, given by Postnikov, that a very constant gain is finite, if and only if the corresponding graph is of finite representation type. This is the only way that this very constant gain ends. On the other hand, Brauer configuration algebras were introduced by Green and Scroll in 2017. And the idea of Green and Scroll was generalizing some Brauer graph algebras. And as Pedro described last Monday, Brauer configuration algebras deal with almost anything in the nature, almost anything in mathematics. Perhaps every field in mathematics is touched by some kind of Brauer configuration algebra. A Brauer configuration algebra consists of quadruples, gamma 0, gamma 1, mu, and O here, where gamma 1 is a finite set of vertices. Gamma 1 is a collection of multisets consisting of vertices. Repetitions allowed are not necessarily sets, but we can repeat a vertex in a given polygon. The mu is a multiplicity function which has as role to include new vertices to the Brauer configuration. O is an orientation given by the polygons where a given vertex happens. We can select the list of the polygons where a given vertex is happening, and we can define a linear order on these polygons, and this defines the orientation. And all this data can be used in order to describe the corresponding Brauer graph associated with this Brauer configuration. This is an example of the quiver associated with this Brauer configuration. In this case, we had two polygons, A31, A32. We had two vertices. I denote these vertices 0 and 1. And in this case, this polygon A31 has two vertices, 0 and 1. And the idea is to describe an arrow between the polygons if this vertex, for instance, the vertex 1, occurs also, or both in A31 and A32. In this case, as you can see here, there are loops. It means that the vertex 0, there is a repetition 3 times of the vertex 0 in the polygon A32. But as you can see here, we see that the vertex 1 is happening in the polygon A31. This is the red line. And also in the polygon A32. And always, you must define an additional arrow in order to complete a cycle. And these cycles are said to be special cycles associated with the successor sequence associated with the weight of the given vertex is happening, or the list of polygons associated with the given vertex. We always complete the successor sequence. These are our special cycles, as I described before. The valency of a vertex is a way or describe how a given vertex is happening in the Brauer configuration. You just count the number of times that the given vertex appears in the different polygons, and you compute the sum, and so on. This is the valency of the given vertex. But the theory of representation of Brauer configuration algebras depends on this combinatorial data. This is our example. There is a way to construct the Brauer configuration algebra by using this algorithm. Firstly, we define a reduced Brauer configuration. Reduced Brauer configuration means that the Brauer configuration does not have truncate vertices. A vertex is said to be truncate if it appears only just once in just one polygon. And this kind of vertices can be disappeared of the Brauer configuration. And we can reduce or delete all the truncate vertices. And when a Brauer configuration has not truncate vertices, the Brauer configuration is said to be reduced. Then we can construct the corresponding quiver, as I described before, define the corresponding algebra associated with the quiver. Then there are some relations, some suitable relations associated with the behavior of the different vertices in the corresponding list of polygons. We define the corresponding biquiver algebra. The biquiver algebra corresponding is the Brauer configuration algebra. And there is a way of using special cycles and corresponding prefixes in order to describe the basis of these algebras. All the theory of representation of Brauer configuration algebra depends on combinatorial data. All the information of the non-truncate vertices. For instance, there is a variation between indecomposable representation of the Brauer, or indecomposable lambda nodules and polygons of the Brauer configuration. These algebras are multiserial, symmetric, and the radical in this case depends on the behavior of non-truncate vertices. It's multiserial. There is a way of defining a formula for the dimension of these algebras. And this symbol here means that we must take the corresponding valency of the vertex in order to obtain this dimension. And since this workshop is on periplectic Lie superalgebras, investigation of Lie superalgebras, I was wondering how I can connect my talk with the investigation of Lie superalgebras. And I read something about the works of Serganova, for instance, Grancharov, regarding periplectic Brauer algebras. This is a very inspired talk given by Grancharov 2 years ago in the online seminar of the Sao Paulo. And there is a way to connect the auxiliary relationship between Brauer configuration algebras and the so-called periplectic Brauer configuration Brauer algebras. For instance, multiplicity function is a way to describe the delta in Brauer algebras. Alex Sierra in 2017 gave the formula for the dimension of the center of the algebra depending on the number of the polygons, the number of the vertices, the number of loops happening in the Brauer quiver, and this kind of vertices which, as you can see here, this vertex is a candidate to be truncated. But as you can see, the multiplicity function is given a number greater than 1. In this case, this vertex is given information about the theory representation of the algebra because the multiplicity is different from 1. Now, we can use the ideas of Berg-Constant's gain in order to describe our word game. But in this case, we will find admissible paths. Oh, excuse me. Admissible paths are boundary realizations of products of linear-oriented linking paths. Right here, G1, for instance. All these paths are labeled by these numbers. But J1, for instance, and we can define some products, A copies of A1, for instance, we can define in this way. The number of copies of this label, linear-oriented linking graph of type A. And also, we can apply a new multiplication. For instance, we can define A1A, a new one. This is J1. This is J2, J1. Here is J2. B copies of a label linear-oriented linking graph of type A. And also, it is possible to define a new product of this form. It's nothing but a linking diagram of type A. In this case, A is greater than 0, B and C is greater or equal 0, and J2 is less than J3. These are the kind of original linking graph that we are, which allows some admissible paths. And the idea is work with realizations in the plane of these products. In such a way that we can obtain, we can interpret these labels here as slopes in the plane of these arrows. Such a way that, for instance, for AJ1, we can obtain something like that, with different slopes in the corresponding realization. And the idea is glued all these paths and so on. But we only do 3 of these products. Let me show you how we can use this one. These are some examples of the way that we multiply realizations. As you can see here, this path with two arrows. One of them is labeled with 0 and 1. This is the corresponding slopes of the arrows. this beta has a slope 0. And we can, for instance, apply the product between alpha squared to repetitions of the path alpha. And we can multiply alpha squared by beta in this way. Alpha q, in this case, this is a repetition of three copies of the admissible path alpha. And this is the way that we compute all the products in this admissible path in the plane. Also, in the case of this realization, we can define some equivalence relation on the vertices. For instance, here we can define or identify the points in the plane by using these classes. These classes are given by this number j. I fit this slope, the same slope, for instance, if the slope is 1, we can take here this type of equivalent classes. If the slope is 1, this is the corresponding equivalent class, and this is another one, for instance. If n is 1. If n is 2, and we cannot define another way of classifying the points on n squared and so on. So we fit this number n in order to classify the points on n squared. Well, these points are equivalent. For this number j, it is possible to define a Brauer configuration. We fit the number j, and the set of vertices is given by the number 0 to bj, where bj is the maximal slope that we use in order to construct the admissible paths. The polygons are nothing but the admissible paths. We define the multiplicity function equals to 3 in order to avoid the presence of truncate vertices. And since the set of admissible paths is finite, we can define a linear order on this kind of admissible path obtained by using this procedure. This is the sample when j equals 3, is the sample I described before. With only 2 slopes, we can obtain this Brauer quiver. It has the same description as I said before. Okay, what is the word game we define here? Some entertainment here. Our word game is played by 2 armies. The army A has as role to protect a region of n squared from launches of the army B. The army B is shooting missiles from points of H0 here, and army A has a GBI, which is a ground-based interceptor, in order to intercept all the missiles launched for the army B. We endowed the missiles of the army A with a GPS in such a way that the machine, the computer, recognizes a missile as an admissible path, as a trajectory. Not as an object, not as an object, but as an admissible path. And the idea is to missiles, the game, Army A protects the region which is called a dome. Dome is also defined by the military. And this is the region. And in this, it finds a admissible path. Missiles are endowed with a GPS device. We define a missile as a missile trajectory. Missiles launched by Army B follows a linear trajectory as in this case. This is a launch from the Army B because we had some point here, H0, and this is a chop of the Army B. And the idea is to establish an admissible path, reach this shot launch from the Army B. It is possible to find out. We end the game once the Army A has been launched all the possible admissible paths, all the possible missiles. Okay? So we can say that, as in the Berkostan case, that a given chop, a missile launched by IMB follows a trajectory determined by a class LJ, as I described before. Then a launch of the Army A is said to be happy if the number of polygons associated with the Brauer configuration J, gamma 1J in this case, is 1. The launch is unhappy if no class of admissible path reaches no trajectory launch from the Army B. And a shot is said to be excited if more than one class of admissible path reaches one class of LG. The problem is a real tricky problem. For which values of n, the slope here, A, B, and C, the copies of these admissible paths, any launch of the Army A to points of classes LJ is happy or excited. This is a very tricky problem. It is very difficult to find out the corresponding numbers here. In some cases, it is possible to find some solutions. In order to find solutions to this problem, we can use this machinery, Cauchy's polygonal number theory and the Ramanujan problem regarding universal quadratic force. Let me recall you that in 1654, Fermat wrote the letter to Pascal, establishing that any integer number can be written as a sum of k-gonal numbers. This is a well-known problem in number theory. Several mathematicians worked in this problem. For instance, we had the famous Gauss-Eureka theorem, establishing that any integer number can be written as a sum of three triangular numbers. And the famous Lagrange theorem regarding the four squares numbers. And also the theorem of Legendre and Gauss, proving that no number of the four or D4 can be written as a sum of three squares numbers. This is a relation between three remarkable mathematicians. Ramanujan, who proposed this problem here, with quadruples of numbers A, B, C, and D in this way, construct an integral quadratic form that it is universal. Any positive number can be written as this sum. Ramanujan proposed 55 of these quadruples. 54 of them were right. And just one, this one, was wrong. Why this quadruple is wrong? Because this quadratic form doesn't represent the number 15. And in this way, Conway, in his seminar in Princeton in 1993, proposed this conjecture. If a positive integer matrix quadratic form represents every number anti-15, then it represents all positive integers. But Conway and Schneeberger never published the proof of this result. This line of investigation finished with the proof of Bargava, who won the Fields Medals in 2014 in Seoul, Korea. Bargava, here, proved this theorem in 2000. But this line on the investigation continued, and we have, for instance, the A theorem, which established which sum of three triangular numbers is universal. If it's given sum of three triangular numbers represents numbers until 8, it represents every integer number. This is a new result in 2010 given by Kane. And this is examples of results found out by different mathematicians regarding the same problem in the last 10 years. But also we have this result of Lubils regarding universal sums of triangular numbers. As you can see here, this 4 is universal if the corresponding numbers A, B, and C belong to this list. And Sun et al. Found out several universal forms for mid-sum of square and triangular numbers, and also here in 2017, the famous 4-square theorem, the conjecture of Ramanujan, and so on. There are many, many results regarding universal quadratic forms. And this is the way of declare winners and losers in our word game, defining by admissible paths, because we prove that the dimension of the Brauer configuration algebra associated with a given number j, where the slope is equals 1, can be bounded by this number, where this number is the number of partition into 3 triangular numbers. But there is not a closed formula for the number of partition into 3 triangular numbers. Thus, we only can bound it, the dimension of these algebras. It is not possible to find out an explicit formula for the dimension of the algebra. We only can bound. Also, by using the relationship between partition into 3 triangular numbers, we can prove that the number of polygons of this Brauer configuration coincides with the number of polygons in this Brauer configuration. This is a relationship between the corresponding partition into 3 triangular numbers. And also, chops or launch from the army A from point 0, 0 are happy or excited if the triple A, B, and C correspond to one of these lists. This is the way to establish is one of the chops launched from the army A is happy or excited by using the Lubils theorem. And also, we can use the A theorem here in order to establish which launch are happy or excited in this case. A, B, and C is A, B, and C for the number j. See, the number j belongs to one of these numbers. We can see that the corresponding chops of the RBA are happy or excited. Now we can extend the problem. We had J1 copies, J1 arrows here, and we can extend this kind of products by using new arrows, labeled in the same way. J1 minus 1. And we call Q star this kind of products. Again, we can, for these extensions, we can define, for instance, products of these four. A1A, extension, for instance, here, J1, J1B, another extension, J2, for instance, C. And what happened where the configuration is given by paths, but extended paths in this way? And the idea is try to establish configuration of A, B, and C, and N in order to find out the way that the army A or the chefs of the army A are happy or excited. Okay, for this particular problem, we obtain this result. Is n equals 1, we can choose A, B, and C from this list in order to establish that the chefs of the army A are happy or excited. And for this case, Q2 means that we can extend two of these products, for instance, in this case. Any J here. In this case, we extend two admissible paths. In this case, we only extend just one path from the original path. And in these cases, we can obtain this result. And advice for RBB. When the chops launch from the army A are unhappy in this case. In this case, is n equals 2, and A, B, and C here equals 1, then launches to classes of point with this 4, with these conditions, of course, are unhappy. And this is the way that Army B succeeds in this war game. So this thought regards some interactions between war games theory, representation theory, number theory, and of course, Lie superalgebras theory. So, thank you all for listening.
Any questions? Comments? Oh, Slav.
Between Brauer configuration algebras and Brauer graph, Brauer algebras, yeah, it's almost the same. Because, yes, I guess that the inspiration of Green and Scroll was precisely peripletic Brauer algebras. I guess that this is the case. This is the same relation. Thank you for the question.
Any other questions? So I have a quick one. It's naive, but anyways. So in the usual classification of Dinkin diagrams of type 80, you say, well, I cannot have these subgraphs that are extended affine ones, but something very special happens, that is that the determinant of the Cartan matrix becomes 0. So you learn something by reaching this extended graph. So I wonder if something similar happens with this Bird's game, the Bird constants game. You're saying it's finite, it doesn't depend on the end vector doesn't depend, but what happens if I play this game on an affine diagram? Is it any different than just an arbitrary extended diagram?
It's not arbitrary, but in this case, we can associate the extension of the Dinkin diagram by associating the way that we can construct square numbers. And it's not arbitrary, but we try to identify this construction with numbers. And this is a different way. For instance, here you can describe this extension as a given square number. And this is the way that we can try to establish what happened with the game. But it's not the same construction with Dinkin diagrams.
No, but before going to this higher version of the, I'm talking about just the usual Bird constants game. Mm-hmm. So if I play it on an affine diagram, this guy is not going to may not finish according to the theorem that you presented. So, but does it happen something special? What happens if I play the usual Bird constants game? I start with a point on an extended affine, on an affine Dinkin diagram.
What happened with the Bird constants game? Okay, this is because, as Irina explained yesterday, Euclidean diagrams are associated with some tame algebras. But in this case, the numbers in the composable representation are covered by some uniparameter families of curves. In other words, the numbers in the composable representation in the tame case can be infinite. But in the case of Dinkin diagram of type A, the numbers in the composable representation is finite. And the way that Bird constant games does not finish is because we can pass from finite type to tame type to an finite number of in the composable to an infinite number of in the composable. And this is the way that, this is the special situation in this case, I guess.
Any other question? All right, so let's thank the speaker again.